All right. So this first page is going to have a whole bunch of ideas on it, a bunch of theorems, and we're basically going to just talk about them, kind of put them in common language, show some quick examples, and then the rest of the lecture is just going to be looking at problems and putting all of those pieces together, okay, seeing how they apply, seeing how we can put them together to figure out problems and stuff like that. So the first question is very similar to one that was on the assignment from 2.2. I actually corrected, I think it was problem 76 on 2.2. I'm not quite done, but it was very similar to this, and the instructions were the same. It says, factor the polynomial and use the leading coefficient and the zeros and their multiplicity, figure out whether it touches or crosses, all that sort of stuff, in order to graph a sketch of this, okay? So I've got this in descending order. So the leading coefficient test, that's a 1 in front of that, and it's an x to the 4th. And remember, x to the 4th starts up here. It can wiggle around 3 times and then go like that. So I've actually drawn it wiggling around a few too many times, so maybe something like this. Okay? That's roughly what it's got to look like. Now, when we go through and actually figure out what it looks like, we're going to factor this to figure out what the zeros are. So I'm going to take this and I'm going to rewrite this as x squared and then x squared minus 4. So I took out the common factor of x squared. That first rule in factoring is always take out the greatest common factor. I'm then left with a quadratic, and I can factor quadratics for sure. I can either use the quadratic formula, or the easiest way to do this is if I can just look at it and factor it. This has 2 terms, has a name. What's this called again? Difference of squares, so pretty easy to factor. So I get x squared, and I get x minus 2, and I get x plus 2. Any questions there? Okay, so let's list the zeros that come from that. Then let's list their multiplicity. And then let's figure out whether they touch or whether they cross. So the 0 that comes from this one is 0. The 0 that comes from here is 2, and the 0 that comes from here is negative 2. What's the multiplicity of this first 0? 2. And the other one's going to be 1. Okay, if it's even, does it touch or cross? If it's even, it touches, and if it's odd, it crosses. Okay, so that quickly we factored it. We figured out what the zeros are. We figured out the multiplicity, and we know whether or not it touches or crosses. So we're going to draw a sketch of this, and we usually want to graph, at the very minimum, accurate x-intercepts, and usually the y-intercept also. So let's mark off where this crosses. Okay, it hits negative 2, it hits 0, and it hits positive 2, and we start up here. And when it hits negative 2, find the 0. What does it do? Touch or cross? It's going to cross. So it crosses through. Okay, then we've got to turn around so we can hit this next 0. Find the 0. What does it do? Touch or cross? It's going to touch. So it's going to come up here. It's going to bounce off there, come down here, and then it's got to cross right there. Put arrows on the end. Label each one of the intercepts. So 2, 0, 0, 0, and this is negative 2, 0. Okay. Now, if we wanted to, we could maybe add a point right here, like maybe plug in a 1 and plug in a negative 1 and see what the function values were. Again, don't assume that that's the very minimum, the bottom point there, so we won't worry about that. And we actually have the y-intercept graphed here also because it crosses at the origin, so that's an x and a y-intercept right there. So that's a pretty darn good sketch right there, and it happens very quickly. Okay, and that's the stuff that we worked on in 2.2. Any questions about that? Okay, and in 2.2 there were a couple other things that we learned. So let's kind of remind ourselves of those. Okay, we learned that factoring the factors and the zeros of a polynomial can make graphing it a lot easier, which is what we just demonstrated there. Okay, we also learned this, and if you'll remember, this was at the bottom of the page, just kind of buried in a paragraph, but this is kind of a big deal, and it's going to be a much bigger deal today. It says we also learned that a polynomial of degree n can have at most n real zeros. So if it's degree 7, it could have 7 real zeros. That's possible. It doesn't have to have 7. It could have up to 7. Okay? And if we allow for complex zeros, if it's degree n, then it has exactly n complex zeros. And that's really what we're going to be talking about today, is we're going to be finding all of the zeros of a polynomial. And some of them are going to get kind of funky, and we're going to use some different tools to figure that out. Okay, in section 2.5, there are a bunch of theorems that are going to make finding the zeros of a polynomial a lot easier. Okay, not easy, because some of these problems are fairly difficult, just easier. Okay, most of the theorems don't actually tell us what the zeros are. They just kind of help us narrow down our search. They make finding the zeros a little bit easier, like I said. Okay? All right. So this first page has a whole bunch of theorems, and each one of the theorems is in a little box. Okay? That's the mathematical language, and then what we're going to try and do is we're going to try and translate each one of these. Okay? I'm not going to prove any of these theorems. Okay? That's well beyond this course. We're just going to take these for granted. These are true statements. So the first one is the fundamental theorem of algebra. Okay, oddly enough, this is the central theorem in algebra. Okay, this is kind of what most things are based on. And it says if f of x is a polynomial of degree n, where n is greater than or equal to 0, then f has at least one 0 in the complex number system. And I just realized there's a typo. That has to be strictly greater than. Okay, that's what I get for not proofreading carefully. So that's strictly greater than 0. So it's got to be degree 1 at least. Okay, then it has at least one 0 in the complex number system. So we're guaranteed at least one complex 0. So if you're working with a polynomial that's degree 1 or higher, we're guaranteed that we're going to get one complex 0. So it's not like we're going to search forever and not find one. We're guaranteed of finding at least one. Okay, this one says if it's odd degree. So if we're dealing with a polynomial with odd degree, and this says it also has to have real coefficients, which we're going to have real coefficients on all the polynomials that we're working with, it says it has to have at least one real 0. Okay? So in other words, okay, you can focus on these guys right here. Okay? If the polynomial is of odd degree, then we are guaranteed at least one real 0. Absolutely guaranteed one real 0. Now, remember what a 0 is. A 0 is a solution, or a root is another word, or graphically speaking, it's the x-intercept. So think about why that is. If I have an odd degree polynomial, why am I guaranteed at least one real 0? Why am I guaranteed at least one x-intercept? Lynn. Sorry. Tammy. Okay, so if the multiplicity is odd, it crosses. That's on the right track. Peyton. That's exactly right. That's it. If you take any odd degree polynomial, no matter how many times it wiggles around in the middle, it's got to start down here and then it's got to end up here. So is there any way it can go from being negative to being positive without crossing through 0? No way. Even if it has a negative in front of it, it starts up and then ends down. It's got to cross through 0 somewhere. Does that make sense? Now, it could cross more than one time, but it's got to cross at least once. Okay? So, do we have the same guarantee if it's even? Raymond says no. Raymond, why do you say no? Why not? Think about what Peyton said. Okay, what's unique about odd ones? They start down here and end up here, or start up here and end down here. Okay, has to cross through 0. What about even functions? Even polynomial functions, yeah. Okay. Right. So with an even one, it would be possible to have one that starts up here, wiggles around and stuff like that, and then goes up and never crosses the x-axis. So we could also have one that does this. So without going from the negatives to the positives or the positives to the negatives, we don't have a guarantee like we do with the odd ones. Okay. Now, a lot of the times we are going to have it will cross, but it is possible. We run into lots of, we've graphed quadratics, we've graphed parabolas that start up here. They have the vertex above the x-axis, so they don't have any real 0s. They don't have any x-intercepts. Okay, we're still going to find the solutions when we're talking about complex numbers, but that's the deal there. Okay, does that make sense so far? Okay, the fundamental theorem here, all that is you can just say, okay, Mr. Laws is not going to give us any polynomials that don't have any answers at all. Okay? If it's odd, we're guaranteed at least one real zero. Okay? And then let's restate the number of real zeros. If it's if we know what its degree is, it can't have any more zeros than whatever the degree is. So this tells us how many real zeros there are and when we can stop looking. So I've got a couple quick examples, and you do actually have some problems like this, or at least parts of problems that are like this. Okay, notice that this says real zeros. Okay, how many real zeros can this have? Okay, and we're going to say it the right way, up to 3. It doesn't have to have 3, up to 3. How about this one right here? Okay, again, say it right, up to 6. And this one right here, up to 1. Now, if we're just talking about real zeros, it can't have any more real zeros than whatever the degree is. So figure out what the degree is. If it's degree 7, it can have up to 7, but can't have more than 7. Okay? Now, the next one says the number of complex zeros, and it says a polynomial function of degree n has precisely n complex zeros. So this tells us exactly how many complex zeros there are and when we can stop looking. So notice the wording on this right here. Okay, these polynomials are exactly the same, but the instructions are just slightly different, and it's going to be really important that you follow the instructions on each problem. Okay, this one said, how many real zeros can it have? Okay, well, real zeros, we're guaranteed at least 1 when it's odd. It could have all the way up to 3. Maybe all 3 of them are real zeros. Okay? But if we're talking complex zeros, it will have exactly the same number as the degree. So how many complex zeros will this one have? 3. Not up to 3. It will have 3 complex zeros. We can find them all. And remember, when we say complex zeros, we're including the real ones and the imaginary ones. Okay? So how many is this going to have? It's going to have 6. And if we were asked to do that problem, we would have to find all 6 of them. Okay? And on this one right here, guaranteed that it's going to have 1. Okay? And we'd be able to find that 1. Okay, any questions there? Okay. So again, front and back of this first page, we're just going through all the ideas. Okay, getting those in our head, and then we're going to practice working with them on the next couple of pages. Okay, so this one says it's the linear factorization theorem. So it says we've got a polynomial of degree n, and I think, let's see, each one of these should be, I think they should be greater than 0, but I'll double check that. Okay, then f has precisely n linear factors. So what this means is, if I give you a polynomial, or there's a polynomial given in the book or in the notes or something like that, and it says factor it, we're guaranteed we're going to be able to factor it. Okay? And we're going to be able to make it look like this. So there might be a number sitting out front, okay, a leading coefficient if you want to think of it that way. And then we're going to have x minus a number, x minus a number, x minus a number, where every single one of those is a complex number. So we're going to be able to factor this so they look nice and neat like this. Okay? So this linearization factor theorem says we're guaranteed that every polynomial can be factored. Every one of them. Okay? And that's our goal today, is we're going to be able to factor these polynomials and figure out what the zeros are. Okay? So I've got a polynomial here, and on these first 2 pages, the problems are relatively simple, just to kind of introduce the ideas. Okay? It says factor the polynomial and find the zeros. And it says factor it completely. So we want to break this down 100%. We want to make it look something like this. So what would we do first on this polynomial if we were going to factor it? Take out the greatest common factor, right? Greatest common factor is x, so I'm left with a 3x squared, a plus 2x, and a minus 1. This is still a relatively easy trinomial. I could write a 3x here and an x here. The only way to make a 1 is to put a 1 here and a 1 there. And which one needs to be negative, the first one or the second one? Middle term has to be positive. Okay. This one needs to be negative. That one needs to be positive. Double check me. These two multiply to be 3x squared. These two multiply to be negative 1. This and this multiplies to be 3x. That multiplies to be minus x. So 3x minus x is positive 2x. So is this the correct factoring? Okay. Now, I could leave it like this, and I could write down the zeros. The 0 here is 0. Here it's 1/3, and here it's negative 1. So there's the correct factoring, and here are the zeros. So we've done a fair amount of this before, right? Any questions on this one? Okay, I want you to watch, because I want to change this just a little bit so it looks more like this right here. You'll notice that on this linear factorization theorem, they've written every one of these as a plain old x. A plain old x plus or minus a number, okay? With a coefficient out front here. What I'd like to do is, I don't like this 3 sitting here, so I'm going to factor that out. So if I take that out, pull that 3 out, I'd be left with an x. And what happens if I factor a 3 out of a negative 1? What's left? Negative 1/3. So compare this to the way we've written this up above in the theorem. Can you see what the coefficient is? Coefficient is 3. If I were to really stretch this out and write it so that we could see what every one of these numbers is, every one of these zeros is, I'd write 3 and I'd write x minus 0. I'd write x minus 1/3 and I'd write x minus minus 1. And then you can see from that, I'm going to blow this up just a little bit. Okay, there's a 0, there's a 0, and there's a 0. Okay. Now, that's kind of a very technical way to go through and do this, but I do want you to recognize that we could pull that coefficient out front, and then we'd be able to look at each one of these and tell, oh, the number with this is a 0, so the 0 that comes from that is 0. This is x minus 1/3, so the 0 that comes from that would be positive 1/3. And this is x plus 1, so the 0 that comes from that would be negative 1. Okay? It's the same thing that we've been doing. It just looks a little bit different, and we're thinking about it just slightly differently. Okay? Any questions? Okay. Doing all right? Okay. A couple more ideas on this page. Okay, that last example was relatively easy. Okay, it's very similar to ones that we've done before. Okay, but this next one, it's the polynomial factorization theorem, and it kind of breaks this down just a little bit more. Okay, every polynomial with real coefficients can be factored as a product of linear factors and something that we call irreducible quadratic factors. So if we take this and we factor it down, what this means is we're going to be able to factor it into linear factors similar to something like this, x plus or minus a number, kind of like what we did up above. It's going to factor into things like that, or things that we're going to call irreducible quadratics. And an irreducible quadratic looks something like this. Now, why would we call this an irreducible quadratic? Because what, Hop? Because it doesn't factor. Can you find two numbers that multiply to be positive 7 that combine to be positive 2? No. Now, does that mean there aren't any answers that come from that? No. What could we always use to solve a quadratic? Quadratic formula. So there are answers in there. It just doesn't factor. So that's why we call it irreducible. Okay? And we'll talk a little bit more specifically about how to deal with irreducible quadratics, and we'll see several examples. Okay? So when we say linear factors, we're talking about x plus or minus a number. When we say irreducible quadratics, we're talking about quadratics that don't factor, okay? Or at least don't factor with really nice numbers like we're used to working with up here, like this one or like that one, okay? Okay, so finding the zeros from linear factors is a piece of cake. Looking at that and knowing the 0 that comes from that is 5 is very easy. Knowing the zeros that come from this, a little more difficult, but again, you can always use the quadratic formula, okay? And many times that's what we'll use on irreducible quadratics, okay? So Let's take a look at this problem right here. Notice how it compares to the one up above. It is almost exactly the same. So if I go through and do this problem, I'm going to factor out an x. I'm left with 3x squared plus 2x plus 1. This is a linear factor. If I had to write it, I could write it as x minus 0 like I did up above. But what about this quadratic? Is it factorable? Not factorable, okay? We're not going to find numbers that multiply to be 3 and combine to be 2. Okay, not going to happen. Okay, but again, are we stuck there? Do we just stop? Nope. What do we use? Quadratic formula. Okay? So it says factor the polynomial completely and find the zeros. I've got one of the zeros and one of the factors. I've got an irreducible quadratic. Let's find the zeros that come from that. So I'm going to come over here and I'm going to write x equals in descending order. So this is going to be a negative 2 for the b, plus or minus b squared. So that's going to be 4 minus 4 times a times c. And you'll remember yesterday I said there were people that made lots of mistakes on this, so please be careful. That's a 3 and a 1, and this is all over 2 times a, so that's going to be a 6. Any questions? Careful here, because this is going to be 4, which, plus or minus? It's going to be minus 12, right? So what I've got here is a negative 2 plus or minus square root of negative 8 all over 6, which gives me a negative 2 plus or minus 2i radical 2 over 6. And let's write down the two zeros that come from that. So these are complex zeros. We haven't come across this very often, okay? The answers to this part of the polynomial, this quadratic, happen to have i's in them, so they're complex numbers. So I'm going to write it this way. I'm going to write it as negative 2 over 6 plus or minus 2i radical 2 over 6. Or what can I reduce here? I can cancel a 2, can't I? So this is going to be negative 1/3 plus or minus I radical 2 over 3. So it said factor the polynomial completely and find the zeros. Okay, so watch very carefully. One of the zeros is 0. Another one of the zeros is negative 1/3 plus I radical 2 over 3. The other 0 is the conjugate of that, negative 1/3 minus I radical 2 over 3. Those numbers right there are the zeros. Okay, now, it said factor this. Okay, writing the factorization when you've got complex zeros is a little bit tricky. Okay, so I'm going to write down that x minus 0. Okay, and again, that's a little bit overkill, but it kind of illustrates the point of how we factor this. Then remember, every one of these is x minus whatever the 0 is. So if I write x minus, let's write down that first 0. Oops, that's a radical 2 over 3. That's what it would be, isn't it? And the next one would be x minus negative 1/3 minus I radical 2 over 3. You with me? Okay. All we need to do is clean this up just a little bit. Okay. I'm not going to bother writing this as an x minus 0 if that's okay. We've kind of illustrated the point. That one is an x. This one is an x. What's minus a minus 1/3? Positive 1/3. And this is going to be minus a positive I radical 2 over 3. So that's going to be minus I radical 3 over 2. Take a look here, minus a minus. So that's going to be, again, plus 1/3. And then that's going to be minus, yes. Oh, because I'm in the habit of writing a radical 3 for some strange reason. Okay. And then minus a minus, this is going to be a plus I radical 2 over 3. Okay, now, take a good look at that. This is a lot of information, and this is quite a bit more complicated than the problems that we've been solving and factoring and finding zeros for and all that stuff. Do you see how every one of these still has the same structure? It's always going to be x minus the 0, x minus the 0, x minus the 0. All we're doing right here is we're just distributing the negative through and cleaning this up just a little bit. Any questions? Okay, take a good look at this. I want you to think about this. Remember, these notes, really, you can consider these part of your homework. So spend a little bit of time thinking about this. I'm going to say this out loud and think about how this kind of has a ring to it. This is x plus 1/3 minus I radical 2 over, whoops, that should be a 3, okay? And this is x plus 1/3 plus I radical 2 over 3. See how that kind of has a ring to it? Kind of just like the conjugates that we were talking about yesterday in section 2.4. Okay, now, any questions on this one? Okay, you'll notice I haven't put a box around this because we're not quite done. You just need a tiny little bit of space up in front of that, okay? So if you did draw a box around it, all you need is a tiny space right here. I want you to take a look at this. When we factor something, you can know whether you factored it correctly by multiplying all these together, and you should get the original polynomial. So take a look at this. Everybody watch, please. You don't need to write anything down. This is thinking. A lot of this section is thinking and putting complicated pieces together. If I took this x and multiplied it with that x, I get x squared, right? If I take x squared and multiply it by that x, what do I get? X cubed. What should it start off with? Should start off with 3x cubed. So remember this right here, where up above we said it can have a coefficient out front, and why I made the point of pulling that out front. Guess what should be out front of that whole thing? A 3, and then it's completely factored. Okay? So all we were missing there was the 3. So once you find the zeros, writing down the linear factors, which is what each one of those is relatively easy. The complex factors are kind of difficult, okay? You got to distribute that negative through, and you get these 3 terms in each one of these. Then you just need to make sure you have the right coefficient out front. Any questions? Okay, let's see. We're getting close to the bottom of the page. Got a couple more ideas to cover. Last 2 theorems, okay? And then the rest of these are just problems that we need to take a look at. Okay, so here's the next one. Okay, that last problem had really ugly answers. Okay, and if you're going to find zeros to a polynomial, it's usually a good idea to find the nicest ones first. Well, the nicest zeros that we could possibly find are what we call rational zeros. They're nice numbers like 2 and 3 and -7. Numbers like that are much better than numbers like radical 3 or 1/3 plus or minus radical 2i over 3 or something like that. Okay, those are pretty ugly. Okay, so we're going to be finding rational zeros using this theorem right here. Okay, now what I'm going to refer to this as, this is going to be the P and Q stuff. And I'll tell you why, and you'll see why in just a second. Okay, this theorem looks really awful. Okay, so here's what it says. If we've got a polynomial that looks like this, okay, take a look at that. That looks pretty horrible, doesn't it? Okay, let's look at this. Again, a lot of thinking here. This is not as bad as it looks. Mathematically speaking, this is how you would write down a normal polynomial. You'll notice that we've got a coefficient out front. And then I've got x raised to the nth power, whatever that power happens to be. Let's say it's 7. So this is the coefficient on the 7th power right here. Look at the next one. This just means the next coefficient. And notice the power. If this used to be a 7, if n is 7, what's the power on this one right here? 7 minus 1, so that would be 6. What's the power on this one? 5, and so forth, all the way till we get down to 2 and 1, and then the last number doesn't have an x on it. It's got an x to the 0, so we end with just that constant right there. So this is a very, very fancy and very ugly way of saying, write down your polynomial in descending order. That's all it means. Okay? But mathematically, that's how we would represent that. So if you've got a polynomial that's written in descending order, and it's got integer coefficients, okay, which is what we're going to have. Okay, we're not going to have any, irrational coefficients or anything weird like that. Okay, then every factor of that, or excuse me, every zero of that polynomial has this form, p over q. A little fraction of p over q, where p is a factor of this one right here on the end, a naught is what we call that, and q is a factor of an. That's this first one right here. So in other words, and you don't have to fill anything in here, P and Q are going to give us a list of nice numbers that we can use to see if they're zeros. We're going to check and see if they work. We're going to check and see if they're factors. Okay? And the one thing you want to note is P and Q is going to give us a list of the possible zeros. It's not going to tell us what the actual zeros are. Okay? So I've got a problem right here, and you literally have some problems that are just like this. It'll say list the possible rational zeros. Okay? So all we need to do to apply this theorem is check and make sure that this is in descending order. Is it in descending order? It is. Okay? P is the number on the end, and Q is the coefficient on the beginning. It's not 2x cubed, it's just the 2. Okay? So here's how we do this problem. I'm going to write P up here, and I'm going to write Q down here, and you'll see why in just a second. So P is a 6. If you want to write -6, that's fine with me. I'll show you how we take care of that in just a second. What's Q? Q is 2. Now, what I want to do is I want to list off the factors of P, and I want to list off the factors of Q. So what are the factors of 6? Or in other words, what numbers go into 6 evenly? 1 does. 1 goes in 6 times. 2 does. 2 goes in 3 times. Anything else? Nope, nothing else. Okay? What are the factors of 2? Just 1 and 2. Okay, now, we're going to make our list of possible zeros. Okay? And I'm going to underline possible. So what we do is we take each number in this list, each one of the factors of P, and we take turns putting it over the factors of Q. So the first thing I'm going to do is 1 over 1. 1 over 1 is 1. 2 over 1. That's 2. 3 over 1. That's 3. 6 over 1. That's 6. So I've taken each one of these factors of P and I've put it over that first factor of Q. Now it's this one's turn. So we're done with this guy right here. Let's do the 2. 1 over 2, 1/2. 2 over 2. 2 over 2 is 1. It's already in my list. Do I need to write it again? Nope. Okay. 3 over 2. 3/2. 6 over 2. 6 over 2 is 3. So do I need to write that again? I don't. Okay. Put a set of brackets around this. And then remember how this one was negative? Really, every one of these could have a plus or minus on it. Okay, because whether this is 6 or -6, a positive 1 and a negative 1 will go into that evenly, right? A positive 3 and a negative 3 will go into that evenly. Okay. Now, I normally don't bother writing them down here. At the end, I come through here and I write a plus or minus in front of every one of these. Okay? These are the possible rational zeros. If there are any nice numbers that are zeros of this polynomial, they have to be on this list. Have to be on that list. Okay? How many numbers are here? there's 3, there's 6 altogether with a plus or minus, so that would be 12 zeros. Is there any way that polynomial can have 12 zeros? No. So do all of these work? No. They're just a list of possibilities. Okay? And you literally have some problems that just say, hey, list the possibilities. Okay? And we'll do another problem like that in just a second. Any questions? Going to take some practice. Okay, let's take a look at the last theorem, and then we'll get to some problems like the ones on your homework. Okay? This is what's called the conjugate pairs theorem. Okay, and it says this: if we've got a polynomial with real coefficients and a plus bi is a 0, then a minus bi is also a 0. They always come in conjugate pairs. Always. So if you have one imaginary 0, you actually have another imaginary 0 automatically. It's got to come in conjugate pairs. Okay? So you have some problems that are literally this easy, so this should be a little bit comforting. Can you name any other zeros of f if two of the zeros are 2 minus 3i and 4i? Well, if 2 minus 3i is a 0, what else has to be a 0? 2 plus 3i. And if 4i is a 0, what else has to be a 0 also? What's its conjugate? Negative 4i. Okay? So if these two are imaginary zeros, we also have to have their imaginary ones. Okay? Now, next question, putting these pieces together. If I have this is a 0, this is a 0, that is a 0, and that is a 0, what is the minimum degree polynomial that could have those as its zeros? It would have to be at least degree 4, right? At least. Could be 5, could be 17, but it's got to be at least degree 4. Why? Because remember, we have the same number of complex zeros as the degree. Look at the bottom of this page right here. A polynomial of degree n has precisely n complex zeros. So if we were going to have 4 answers, which we had on this one right here, it's got to be at least degree 4. Okay? Make sense? So I'll put at least degree 4. Okay? Now, this section, if you go through and read it, is extremely long. Okay? I think it's like 12 pages long or something like that. It has 2 other theorems in it. One of it is called Descartes' rule of signs, and the other one is called the upper and lower bound theorems. Okay? It's not that these aren't useful. They are useful. The college doesn't teach these in Math 1050. Okay? They can save some time, but they're not as useful as the theorems that we've talked about already today. So we're not going to cover those. So if you see a problem in the assignment that says use Descartes' rule of signs or do the upper and lower bound theorem, which reminds me, I think the last 2 problems, 80 and 81, I think you can cross those off from the assignment because I think I circled those incorrectly. Okay? I think they ask you to figure out what the upper and lower bound is. If you're interested, you could read it. You can also find some videos on the internet that talk about how to do that. Okay? All right. Go ahead and flip the page over. We've got about 8 minutes left. We're going to do some problems very similar to the assignment. Okay? This section basically takes all of these theorems, and we've got to combine these ideas and use our heads. Okay? And that's going to kind of be a running theme with a lot of the stuff that we're going to cover over about the next month. You've really got to have your head on straight and think about how the pieces of these puzzles fit together. Okay? And that's really the value of math, is being able to figure out complicated stuff like this, taking the small pieces, putting them together to make up the whole picture. Make sure you pay attention to the instructions. There are problems that say find only the real answers. That's kind of good because then we don't have to worry about anything with an I in it. If it says find all the answers or find the complex answers, then you've got to find all of them, including the ones with I's in them. Okay? All right. So, like I said a second ago, you can consider these part of your homework for the section, because if you look at the homework, I think you only maybe signed the 10 problems or so, maybe a dozen. Okay. It says find all the real zeros of the following. Okay, well, what's nice about this? What's that? What's nice about these? No, I hear it. Somebody's whispering. What is it? It's already factored. Already factored. Well, at least this one's factored, and this one's factored, and this one's factored. We'll take care of that one in just a second. The 0 that comes from here is 0. The 0 that comes from here is -4. What's the 0 that comes from here? 0 that comes from there is 7. It happens to be a double 0 or a double solution. Its multiplicity is 2, but it just said, what's the 0? How about this one? Okay, if we were going to solve that, you could use the quadratic formula, or you could just do this. When does x squared minus 5 equal 0? When x squared is equal to 5, which I take the square root of both sides, and I end up with plus or minus radical 5. So I get plus radical 5, and I get minus radical 5 there. Okay? So there are all the zeros. And are all of these real numbers? Yes, they are. So I do need to find all of those. What's the 0 that comes from here? 0. What about from here? Well, if I do this the same way, if I set this equal to 0 and then I solve that, I'm going to get a -9 over here, and then I'm going to take the square root. Am I going to get real answers? I'm not. So these are not real. So the only real answer from this one is just 0. If you wanted to finish this off and write plus or minus 3i, that's okay. I'm actually going to use that in just a second. Any questions there? Sure? Okay, take a look at this one. It says find all the zeros. Now, if it says all the zeros and it doesn't specify real zeros, should we find the ones with I? Yes, we should. So what's the 0 that comes from here? 0. From here? -I. From here? +I. And from here? Well, gosh, I think we saw this just a second ago, didn't we? Let's break this down a little bit more. The 0 that comes from here is 2, and from here, -2. There are all the zeros, including the complex zeros, the ones with i's on them. Okay, so let's take a look at this example right here. The instructions are different now. It's the exact same problem as up above, but the instructions have changed. Now it says find all the zeros. So the 0 that comes from here is 0. What's the 0 or the zeros that come from this one here? Plus or minus 3i. So I've got 0, I've got 3i, and I've got minus 3i. There are all the zeros on that one there. Okay? Any questions? Okay, so a couple of thought questions on this. It says, look at the quadratics in the last 2 examples. So look at these 4 examples right here. Do you see a difference between the quadratics? So take a look at the quadratics. There's a quadratic here, 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 and here. Of course, this is the same one. So there are 3 quadratics listed here. Do you see a difference between each one of these? I see some shaking heads yes, I see some shaking heads no. Okay, there is a difference. Okay, the difference between these two is this one factors using nice rational numbers. This one factors, and if you think about it, it would factor to x minus radical 5 and x plus radical 5. It factors over the irrational numbers. So it's not what we typically factor. We normally wouldn't factor something this way, but doesn't that work? That's a perfect square of radical 5. Just like that's a perfect square of 4. So this is going to be x minus radical 5 and x plus radical 5. This one is an irreducible quadratic. Okay, and if we factor it over the complex numbers, here's what it would factor to. Okay, this is a perfect square of 3i. So this is going to factor to x minus 3i and x plus 3i. Everybody catch that? if we were asked to factor this one completely, this is what it would factor to. And you're going to be asked to factor some problems like this completely, and this is what you do. Find all the zeros, like we've done several times already today, and these are the factors that would come from each one of these zeros. So these are irreducible quadratics. They don't factor nicely. This one factors using irrational numbers, and this one factors using complex numbers or numbers with I in them. That might take some thought to think about and figure out how does all this stuff fit together. Okay? Any questions? Okay. Let's see. Let's do this one last problem, and then we'll call it quits for today. And then what I'd like you to do is I'd like you to go home and read the notes again, think about them. If you need to watch the video again, please do that. Okay? You've got a problem. This is problem number 10. It's on your assignment. Okay? Or it's almost identical to one on your assignment. Okay? It says use the rational zeros. Now, if I say rational zeros test, you think P and Q. So on this problem, what is P? P is the number on the end. Okay? Whether you use the sign there or not, I don't care. What's Q? 4. Okay? Write down the factors for each one of them. 1 and 2. 1 and 2 and 4, right? Let's start our list. Our list is going to be 1 over 1. That's a 1. 2 over 1. That's a 2. 1 over 2. 1/2. 1 over 4. Or sorry, let's do 2 over 2. 2 over 2 is 1. Okay? Then 1 over 4. That's 1/4. And then 2 over 4. 2 over 4 is a half, right? It's already on our list, so we don't need to worry about it. Now, once I make this list here, what else do I need to add at this point? Plus or minus. These instructions are literally taken directly from the book. It says, use the rational zeros to list all the possible rational zeros. I've listed all the possibilities. And then it says, verify that the zeros shown on the graph are on the list. Okay, look at the scale. Let me blow this up just a little bit. What's that 0 right there? -1. What's this 0 right here? 1/2 right here. 1. And what's this one right here? 2. So I've got a -1, a 1/2, a 1, and a 2. Are all of those on the list? Yeah. Oh, there is. Thank you very much. Yeah, I missed that one. -1/2. Thanks. Those are the zeros that you can see on the graph. Are they on our list? Yes, they are. That's all you have to do. List them and then look at it. Okay. Spend some time thinking about that. If you need to watch the video again, please do. Tomorrow we're going to do the rest of the problems in the notes. Friday's review, Monday.